Hey everybody, it's Adam again and welcome back to my garage. So if you've been following along the last couple of episodes, we've been digging into the ATC 300 transfer case for Project E36 XTI. Today, instead of getting down to the motor level, we're going to reassemble everything back to the transfer case and really start digging into the system characteristics in terms of how much current the motor pulls as it's going from 0 to 100% lock, and also the sensor feedback. Also off camera the last couple of weeks, I've been mulling around some ideas for pseudocode and how we're going to program the PIC processor. And as you can see on the bench, we've added a couple new tools. So before we dig into that transfer case, hopefully for the last time today, we're going to go ahead and show you what else we've picked up on the bench here, and I'll walk you through some of the new tools we've added to the garage the last couple of weeks as well. Come along for the ride. Let's take a look at the tools we'll be using today. So as you remember from the previous episodes, we've got the schematic here, and that's where we got down to the circuit level in terms of the sensors and how the motor is being characterized. If you remember in the last episode, we stopped at basically getting the stall current for the motor because it was greater than 10 amps, greater than what our little multimeter could deal with. We've got our power supply here, the nice big battery that we use actually in the E36. That'll be powering up our board as we go through and do some more evaluation today. We've got the PIC programmer down here. So that is a PIC kit programmer knockoff that I got off of Amazon. We'll be using that to program our PIC 16F684. Down here, we've got a current sensing module. So this is like a Hall effect current sensing module, which can get us up to 30 amps of resolution. We've got the PIC 16F684 itself, so a little 14-pin device, just enough pins for what we need to use for this project we're doing here. Let's take a look up over here. New addition in the last week, we got this Tektronix TDS 2002C, and basically it's a 2-channel oscilloscope. We'll be digging into that today as we look at the sensor feedback and the current measurement. Also, as you saw in the first episode, we had this function generator in the background. Once we get into PWMing and testing out the different levels of frequency and modulation on the motor itself, we're going to dig into how far this thing actually has to go from 0 to 100% lock. Over here, of course, we got our breadboard. You saw that in the last episode. Got the 5-volt power regulator on there. We're going to use that for driving our sensors. And I've got some additional 5-volt power supplies over here, and also some additional FETs in case we need it for any other sort of signal related things. Down here we've got a temperature sensor. We're going to use that when we go to stall the motor and see how much she heats up. And of course we got our trusty voltmeter back here. Take a look over here. Been working the last couple of weeks on how are we actually going to set up the code in the PIC processor. Done some pseudocode over here, and that's what's going to be the brains behind the organization. Leave a comment down below if you're interested in seeing the software and how we do this, or if you just want me to jump straight into building the hardware and installing this in the vehicle. And then, of course, last but not least, we've got one beer here. Hopefully what we do tonight will last basically through the one beer. If not, I'm sure I've got some other beers hiding around in the garage somewhere. Super stoked because now we're taking this thing back to a system level. We're going to reassemble this actuator and gearbox back to the transfer case and get into really characterizing what we're going to do at a system level from a control scheme perspective. Also, I got to hand it to user Psychopateful for simply saying oscilloscope. And basically that is what prompted me to recognize, yeah, it was time to go ahead and upgrade the equipment on the bench here. So if you guys think I need to get additional tools or do something different, leave a comment just like Psychopateful did, and we'll take a look at whether or not we add that to the toolbox here. You're probably thinking enough jibber jabbering, Adam, let's get down to business. I agree, so let's dig into this thing. All right, so the first thing we're going to do is get this actuator put back together here, and then we're going to bring the transfer case back up on top of the bench here, and we'll start hooking it up to the oscilloscope and the power to figure out how we want to go ahead and measure this thing out today. Something you got to be mindful of as you're putting these screws back on here to get the motor reassembled is the torque on these things is so precise that if you don't torque it correctly, you know, this whole thing could just, I don't know, explode in the car as you're going from 0 to 100% lockup. So we're going to be extra careful with this some other time in the future. I will probably forget actually to torque these properly once it's in the vehicle, but I'm willing to take my chances because this thing seems to be so delicate, so precise, that not torquing these properly should have minimal effect to what actually may happen later. Let's do a quick sense check here. We're going to go ahead and put red on the orange, and let's touch it over here to the, whoa, we don't want to do that yet. Touch it over here to the black wire, and let's just make sure that, there we go. So the motor is actuating the way we expect it to. Everything sounds good. Let's get this thing assembled up over to the transfer case. Now, if I just put my tools away, I'd be able to find the nice inverted Torx to screw this guy back on here. But I'm going to have to go on a treasure hunt. Let's see what we can find. Of course, it'd be hiding underneath the schematic and all the other stuff I just moved around. All right, back in business here. Again, the torque is probably pretty important on these, but we'll worry about that later. So just a little sense check here. Once that actuator's back on there, we've got effectively, I don't want to crush my little pick processors. So we've got effectively a 0% lockup on here right now. This is the output shaft to the rear wheels here, and then this is the output shaft that goes to the front drive shaft up to the front differential. And you can see it's pretty easy. I can spin these independently. If I got no load on the front, they go together, but by hand, I can hold these two things effectively independent. So what I'm going to do here, I'm just going to apply straight 12 volts to the actuator. That should lock this thing right up. And if this transfer case is any good, I should be able to move these in tandem without holding it back over here on the front output shaft. We're going to hear this actuate as soon as I touch the black wire over to the ground path. And hopefully I don't break something. I don't even know if this is how this is supposed to work, but I think that, but logically it should work this way. Let's see. Here we go. Okay, so the motor's locked up right now. We got 12 volts going to this. You could hear it lock up. And, oh boy, yeah, well, geez. Oh boy, she's locked up completely. And there's basically no movement whatsoever. So that clutch definitely locked up here with the input shaft from the transmission. And that's interesting. Motor isn't really getting warm. But what you just heard right there, when I let off of it, it actually opened up the diff here. So that is pretty interesting to me that you could actually hear the diff unlock as soon as I unpowered it. So one of the theories that I mentioned in the first or second video was I was thinking that this clutch mechanism inside of here has enough mechanical advantage over the actuator to where you could back drive the actuator. And just by unplugging it there, we could hear the actuator actually move back. So it wasn't being powered in the negative direction at all. And effectively, we've got the open diff situation again. So the good news at least is when I put the power on it, it locks it up a little too much. Probably won't be able to run a full 12 volts on this thing when we've got it in the vehicle. We're going to have to find that PWM balance in between so we don't completely lock up the transfer case. But the good news is as soon as it's unpowered, it goes back into the open state like we were thinking before. I talked about it a little bit in a previous episode, but one of the big things that could complicate this control system would be as if we had to apply a negative polarity to this when we're switching it back and forth. So that's why it's really important that this thing goes back to a home position just mechanically by itself. We only have to worry about powering this in the positive direction. And then when we PWM it, so we're going to send a frequency to it that basically acts like variable power going into the motor, we should be able to go anywhere from 0 up to 100%. The next thing I think we're going to do before we plug in a FET and start to do PWM with the function generator here, we're going to go ahead and check and see what that current is when it stalls. Okay, so what we're going to do is we're going to take our little current sense module here. This is actually a 20 amp range module, and effectively what you do is you run the ground wire back to the battery on one end of this, and then you run the ground wire to the motor on the other end of this, and then power just connects up to the battery on the other side. This has 100 millivolts per amp, so effectively when we get to, let's say there's just 2 amps being pulled on there, that's 200 millivolts. When we get all the way up to 20 amps with this, that would be a 2-volt signal effectively coming off of our outline here. VCC is a 5-volt signal that we're going to go from the regulator on the circuit board, and then ground we're also going to connect over back to a clean ground that goes directly back to the battery there as well. So let's get the wiring up on this, and then we'll hook up basically the output to the oscilloscope, and we're going to monitor what kind of current we see coming out of this once we run this motor all the way to stall condition. Okay, we're going to do a quick wiring check on here just to make sure that we've got 5 volts coming off of our regulator circuit. In fact, I'm so excited to use the oscilloscope, I'm not even going to use a multimeter for this. I want to take a look and see if we get a nice, clean 5-volt signal coming off of our regulator. There we go. Okay, so channel 2, we've got a 10-volt scale. That doesn't make any sense. Why do we see 12 volts coming off of there? Well, nope, just a minute. That's, you know, it's been too long since I've used one of these oscilloscopes. I think I need to go back to school and figure this out. But basically, on the blue line there, that's where we've got our 5-volt signal right now. We're going to change the 0 position here to right about there, and then we're going to change our scale to be 5 volts per major division here. So right now, we've got a nice clean 5-volt signal on our blue line there. There's the 0 voltage line, and then that's at 5 volts right there. So we're going to run this 5 volts. Let's see here. I will run the 5 volts right down to this line over here. So we've got a nice power rail that's got 5 volts on it. You know, they don't make these jumpers like they used to. I tell you what, nothing is made like it's used to. Okay, and we're going to go ahead and plug in our little jumpers over here. We've got VCC, which is our 5 volts that I just put together. And then we're going to connect ground back to our ground rail over here, and look at that. So we've got the red light on the sensor board here indicating we've got the right power going to it. The next thing we're going to do is we're going to run another jumper off of here over to the oscilloscope. We'll keep that, I think, channel number 2. We've already got that set up there to run to 5 volts. It's actually right at 2.5 volts right now for signal number 2, and that's really the nominal that it ends up at because it can measure both positive and negative current. So it goes up and down from there, 100 millivolts per amp. You do the math. I can't do it in my head right now. Next up, let's go ahead and get our ground wire plugged into the module over here. And we got this big old transfer case we've got to contend with, but I'm okay with that. I think get that wire assembled into our terminal here on the current sense. I guess we're taking a chance here, assuming that this motor is going to pull less than 20 amps. If it pulls more than 20 amps, we might have a problem because I'm not going to be able to measure the current on this. And then I'll have to go ahead and order a 30 amp module for this. Now, there we go, okay. You know, for safety's sake, I think what I'm going to do is just leave that plugged in, because if something shorts out, we'll just have something burn and start on fire here before we are able to react quick enough to fix anything. Yeah, but I don't like that I got this signal just seems to be a little intermittent there. I don't know what's going on with that, but hey, we'll deal with it. That's life. You know, I'm not using medical devices or anything like that here. This isn't exactly precision equipment. We're just trying to make xDrive work for Project E36 XTI, of course. Okay, so now we've got the ground wire is hooked up there, the ground circuit itself. And what I'm going to do is I am going to run this right down to the board here. We've got this nice this nice fitting on here, which we might be able to actually get our wire through the hole and fasten this guy down. We got that close enough there. We still got ground here. That's good. Okay. All right. Oh, geez, we got an oscillation going on here. Let's get this guy tied back here, and let's see what happens with that signal when we do that. There we go. Oh, no, geez, you know, if I could just get this thing to clip on here. That's it. All right. So we're back to a nice clean signal coming off of there. Now we can go ahead and get the ground wire for the motor plugged back in, and then we're going to go ahead and power this thing and watch what it does on the screen here. We're all set up on the oscilloscope over there. We're going to go ahead and plug in the red wire now to the motor. We're going to let this thing lock up, and we're going to watch what happens on the screen here. So right now, channel 2, we've got 2 volts per division, and basically we've got 2, 4, 6. Let's go ahead and plug in the red wire now, and let's see what we get coming off of this guy. And I'm going to be ready to stop this as soon as it stalls out, because what I'm going to want to see is where that current ends up. There we go. Stop, and I'm going to disconnect. Look at that. All right. So you can see where we ended up powering the motor there. Something smells warm, but I don't see anything smoking, so that must mean we're in good shape. But basically, when we say we've got 2 volts per major division here, effectively we got 2, and we went to 4, and that went straight up to 5 volts there. So we maxed this thing out, and basically that means we got more than 20 amps coming off of this thing. I don't know if I like that. But at the same time, actually, I can see when it was actually going between 0 and locked, you know, you've got an initial spike there at the beginning to get the motor moving. But as it was actually transitioning from 0 to fully locked, it was down low quite a ways there. So the running load on this wasn't so bad. This might actually work out for what we needed to do. I just want to make sure that I don't overload that 20 amp chip on there, and for some reason, if we end up overloading that, we might actually burn something up. But let's take a deeper look here and see what happens when we actually watch this thing transition from 0 to locked. All right, let's go ahead and run this again, and I'm going to be ready to stop it again here. Oh, got so excited that my function generator stand delatched underneath there. Oh my goodness. This is just falling apart here. So if we take a deeper look at this, you can see again where, oh shoot, I got smoke coming out of here again. Yep, see, there's some magic smoke coming out of there right now. That's, we don't want that to happen there. I don't know what is smoking right now. I think it's that terminal is actually smoking. Yeah, look at that. It just desoldered itself. Yeah, thought I could smell solder. So, you know what? I may just have to go back to the drawing board when it comes to what chip I'm going to use on here, because that guy got heated up. And one of the things that we're going to do as part of the routine on this is when we do a startup routine, you first key on. Basically, we want to run the motor into a full stall condition. Oh, gee, well, you know what? That's why I left the thing attached for too long. She heated up on there, and naturally it started desoldering itself. So I guess the good news is we didn't actually start anything on fire. The bad news is we can't let this thing stall for much longer than a second or two, because what's going to happen is that thing is going to burn up and desolder on us there. So we got more than 20 amps coming out of this baby when we lock it up. But anyways, let's go ahead and take a look at what we've got going on with the signal here. So on average, that was about let's just say that was at 1.2 volts. So when we set our nominal is 2.5 volts on this, why it's, you know what, geez, I'm getting ahead of myself. Starting back at square one. All right. So let's take a look at the oscilloscope screen and see how the motor reacted when we ran it to the stall position. So, as you can see, it looks like we maxed out our current sensor. Basically tells me that when you run this thing up to a full stall, she's pulling more than 20 amps. So we might need to consider getting a 30 amp chip. But at least for now, we can still get some useful information from this. And we're going to zoom in just a little bit here, and let's get this to a little bit different position. So let's talk about the characteristics of the motor motion here. You can see we weren't plugged in here. As soon as we plugged in the 12 volts, it shot up here to maximizing it. So basically the initial current to get the motor moving goes up to a instantaneous stall, and as it starts moving, that current comes down. And as it was running to go into a full lock position, let's see what that running current was. I mean, that was only about maybe 2 amps, 2.4 amps. Remember, it's 100 millivolts per amp. So we had 2.4 amps of running current. That's good. That's nice to know. And as it ramped up into being locked up completely, you can see that it ramped up over the course of, let's see, 100, maybe 150, 140 milliseconds here. It went from pretty much open all the way up to that fully locked position. Again, we had some transit across here though, so if you think about this being fully open over here at 0%, it goes 100, 200, 300, 400, so that on both ends, about 500 milliseconds from start to finish here, open to closed. So that's good to know as well. We're going to go ahead and write that down because that's good information. Okay, so our max current, max stall is, we said it was greater than 10 amps the last time. We're going to say it's greater than 20 amps this time. So that tells me I got to buy a 30 amp sensor. But the good news is it's effectively 500 milliseconds from 0 to 100%. And I would just say 100% is still somewhat to be determined, because as we saw when I did it manually before we plugged in the current sensor, when that thing is locked up on here, it basically locks up the whole gearbox. So we need to end up somewhere along that slope there as it's, you know, locking up its position. So it's 500 milliseconds from 0 to 100%, running current under kind of a freewheeling. We said that was 2.4 amps, I believe. And I guess we'll take the max out of that because there's a little bit of noise there. So it ends up being 3.2 amps, 2 amps of running current. All right, so let me show you the FET that we're looking at using on this. This is an AWD E36 which is good to up to over 60 amps. So that's good. Probably would have to put a heat sink on it if we were running at 60 amps for a long time. Since we're running in the 20 to 30 amp range for now, at least for exploring the PWM this evening, we're just going to go ahead and wire up to these pins directly and then effectively have the function generator drive the gate pin on here as well. So something we're going to do, we're going to actually plug in channel 1 to our PWM signal so we can monitor the duty cycle coming off of the function generator. And then we're also going to add a, I don't know, maybe a 1K resistor in series with the signal wire coming out of the function generator, just to protect that guy in case this FET blows up on us down here and shorts something out. We don't want to fry the circuitry inside of our function generator. Even better, let's use a 10K resistor on there. So we've got the oscilloscope set up here. We've got our function generator output down here going over to the gate. This red line actually is going over to the gate of our transistor down there. And we have our channel number 1 probe coming off of the function generator. So as you can see right now, it's let's see, we've got it at the lowest duty cycle that our function generator will go. We've got it on a square wave because it'll be a digital signal, but it's running at basically 5 volts there, and maybe that's 20% duty cycle. The blue line, as we had it before, is still our current that's coming off of the motor, basically the current going through the motor. Right now we have no power going into the motor. And what we're going to do is we're actually going to plug in the power now. We're going to see what happens with our little low side driver there. And hopefully nothing burns up immediately. I guess we'll see what happens. Fingers crossed. So right now we got the open transfer case again. I guess let's just see what happens when we plug this guy in. Oh gosh. There we go. Okay. So listen to that. You can hear a buzz, actually, that's coming off of the motor. I'm going to move a mic down here. That's exactly what we expect, is to have a little bit of a buzz coming off of there, because you've got basically this 154, 155 hertz signal going into the motor. I got smoke coming out of here somewhere. Where do we got smoke coming? That might just be, let's see, it's our, oh, okay. She just crapped out on us there. So our 60 amp FET seemed to not like how fast we were switching that there. And I wonder if we burned up our FET, because she got pretty hot. I think what I'm going to have to do is maybe lower our frequency a little bit there, just because she's probably doing a lot of work to switch on and off that fast. So we're going to lower our frequency. Got so hot that it actually desoldered itself down here. All right, let's go ahead and, let's see here. Looks like we lost, okay, so I think our FET probably failed on us here. We're going to have to go ahead and switch up to a different FET, see what happens. And I'm glad we put that resistor on there, because if we didn't, we probably would have blown up our function generator over there. That's why I got 10 pieces of these little guys, because if I didn't have 10 pieces of these, I would burn up the first one and we would have to call it a night. But we're not finished with this first beer yet, so we're not calling it a night. Okay, let's try round 2. So we've got it really now only at about 16, 17 hertz. I'm going to get out my little temperature gauge here and just read how this FET's doing. Yeah, see, I don't know why I keep on burning it up. But she's getting hot. Let's check the data sheet out on this thing and confirm that we got it plugged in properly here. That gate signal is getting hot on there to the point of where it desolders itself. I don't understand why it's doing that. So we switched up the current monitor to be above our low side driver here, because I'm wondering if that low side driver isn't really getting a good true ground through that current monitor. And we'll see what happens this time around, but this is FET number 3. And if I burn this one up, just about done with this first beer, I think we're going to call it a night. So I'm getting a nice pulse out of there. I can hear the motor pulsing in here. The problem is when it sits like that for a while, it ends up burning up the FET after a couple minutes. Right now, oh, she's smoking again. So it's definitely PWMing the motor. The FET definitely doesn't like it when she's getting warmed up there. So I got to figure out what's going on with these FETs, why they keep blowing up. Because I do get a nice 5-volt signal coming off of the function generator, which should be more than enough to bias this thing. So you can hear if I slow down the frequency enough to where it's basically a pulse a second, we're getting the motor actuating in there, and then it winds down. So I know that that FET is doing what we want it to do. It's powering the motor the way we want to power it. But for some reason, it just seems that we end up driving this guy straight to craziness. Maybe we have the frequency too low. I don't know. Let's go ahead and just bump this thing up to, let's say, like 10 kilohertz here, and let's see what happens. So here's the chart. Let me show you the chart here. When we just had it running at 1 hertz, and you can see the current spikes in blue there when it powers it, and then when it lets off, the current drops down. But it's basically going from 0 to full lock the whole time, as you could hear. We just upped the frequency on it here to 15 kilohertz. And let's see if we can get 15 kilohertz to act any differently for us. It's kind of weird. We do have a sawtooth there. I don't want that. I want a nice square wave coming off of there. I wonder if we already fried this FET. I think our FET is having a problem with switching. Okay, so I've pretty much minimized what I can do with the duty cycle on this function generator here. Basically, you can see on the measurement side of things over here, we're down at a 19.4% duty cycle, and we're running at about 70 hertz, and I've upped the max of basically the gate voltage on the low side driver just to make sure that we're making sure that we fully saturate this FET as we're powering as a low side. And effectively at 19% duty cycle, the actuator still goes to a full lock position. I know it's PWMing it because you can hear it buzz. You hear it buzzing. But you can hear that it's indexing all the way to full lock. So I got to figure out this duty cycle or something. I got to figure out what minimum duty cycle gets this guy to kind of operate in a 0 to 100 range. Because right now we're unlocked again here, and if I hold this part here, you can see that it's unlocked like it was at the start of the video. And then when we go ahead and hit this guy here, we'll do it quick, it locks the whole transfer case up when you end up getting to that point where that motor has actuated all the way. So we're going to have to go back to the drawing board. I got to dig into this a little bit more. The duty cycle on this thing has got to be less than 19%. And in my mind, something isn't adding up, so I got to dig into this a little bit more. So we got this first beer down. I've spent enough time on this tonight, and we're going to go back at this again tomorrow after I do a little bit of research online. Let's see what we can find, but ultimately we got to dig into what this minimum duty cycle is for this actuator. Okay, boys, it's time to bring this thing home. So did a little bit of thinking and consulting some consortiums of experts, and I've managed to blow up this FET now 5 different times. We got the graveyard over here, and basically what's happening is the FET's overheating. I don't think because of overcurrent, but I think because of the switching that we're doing with the PWM and trying to control it with the function generator. So we're going to try to make this FET last. We're going to put a heat sink on it if I can find a piece of material around. And I also did a couple of different things like adding a flyback diode across the motor leads to help suppress some of the electrical pulses that come off when you actually disconnect from the function generator when it goes low. And I also reduced the gate resistance of the signal going into the FET. And that way the function generator does more of the work to shift it up and down rather than the FET trying to pull it down to ground all the time. Let's take a look at what we did with the circuit here, and then we're going to dig into playing with the frequency again. Pardon the mess, but since I'm always in a rush, I just basically throw this stuff together, and in my mind it all makes sense. So what we did is we see that diode right there in the middle. Oh, that diode, that little black diode right there, basically goes from the ground side of our low side driver over to the high side. The diode is going from ground to the high side and effectively suppresses any voltage spikes that come off of the actuator as we're switching it. The other thing too is this alligator clip here that goes into the gate of the transistor, that's coming directly off of our function generator down here. I also have it at a low resistance, so it's at a 50 ohm impedance down there, so we've got a nice low gate resistance. And let's see if we can find a heat sink around here somewhere. So amidst all the garbage, there's this little, I don't know, thin piece of galvanized steel here. That ought to be good enough. We'll just clamp it down to the body of their FET here and see if that dissipates some of the heat for us. I don't know why it's got oil on there. It's interesting. And we're going to get real scientific about how we connect this to our heat sink here. I did have an alligator clip laying around a second ago and I lost it. There we go. Okay. So let's, you know what, that oil actually might help it with a little bit of thermal conductivity there. So we'll just smear a little bit down here. And very carefully, we're going to take this alligator clip and affix to the body of the, oh, I don't want those to touch. Affix that to the body of the FET. We'll just put this pen in between here. There we go. Okay. All right, so we've got, no, we don't. Perfect. Okay, so we've got our heat sink set up on here. We've got the function generator plugged in there. And basically what I've been doing is over on the function generator, there's an attenuation button on here. And whenever I want to turn the PWM on and off, rather than turning the function generator on and off, I just hit this attenuator, and it basically shifts the gate drive magnitude up and down there to the point of where the FET isn't even switching right now. But when I turn it on, as you can see, we start pulling current up there. All right, so right now, just by running it that little bit there, I've managed to lock the transfer case up. So something else I've learned here is that when you apply the PWM, it'll run it into a full lockup type position. Like right now, these are completely coupled together. It'll run it into a full lockup, and what it takes is a little bit of oomph in the direction of locking it up more, and then it springs back on its own. So maybe you'll be able to hear this as soon as it springs back. She's fully locked up because when I just turned it on to demonstrate the attenuation on the function generator, it ran it up into the lock position, but there's nothing to help it get back to the home position. And now there's no oil inside this transfer case either, so we're kind of running this dry right now. But, yep, it basically stays in that position there, and she's stayed nice and locked up. So one of the things I think we have to do is effectively what I do here. I turn that on and I put it, there you go. So you could hear it actuating. If I go ahead and move the frequency down here to basically 1 hertz, it's like running a DC signal in it for maybe a second or a fraction of a second. And you could hear it actuating going zzz, zzz, zzz. When it dials it back, you could hear it kind of unload. And right now, it should be unlocked, yep. So right now, I can completely move these independently. There's still a little bit of resistance there, but the more you work this, the more the clutches decompress, and the lighter the lockup actually gets there. So right now I would say we're at a home position in here in the transfer case, and we're going to go ahead and see if we can get this PWM to kind of get us to something that's a little more locked than this, but not fully locked up. So I'm going to go ahead and move my frequency back up to about 130 hertz is what I'm running the frequency at right now. And I'm going to turn the duty cycle all the way down. So we're about 19% duty cycle with that PWM. And I'm going to go ahead and turn off the attenuator here. And we might hear it actuate just a little bit. And you're going to hear a little bit of a frequency noise there as well at about 130 hertz. Here we go. So, yep, now she just completely locked up on us there. So we're going to turn this off again. And we're going to have to run her back home again too. There we go. So, yep, now she's unlocked there again too. So, again, it's back driving, it gets unlocked. Let's see if we can get it somewhere a little bit more or less where it's at right now. I'm going to bump this frequency up to 1.3K this time. Let's see what happens. So you can hear that. Still unlocked. That's good. We like that. I'm going to change the duty cycle just a little bit here and see what we get. Still unlocked. There we go. She's actuated. Okay, now she's locked up. Yeah, it's completely locked up again, but we still have motion here, which is good. Doesn't take much. And our FET's getting warm down here. What do we got? Yeah, she's at about 96, 90, 94, yeah, 93. So our heat sink is warming up on us there. So we're still getting a lot of heat coming out of that FET just from switching. I don't want to blow up another FET here either. So I'm beginning to think that PWM may not be the way to go with this. Now one of the fans of the channel had actually left a comment on my older video that he had done some probing on the ATC 35L and noticed that the DC signal was basically just pulsing the actuator to get it to the position it needed to be. So if PWM isn't going to work for us here, which the more I work on this, the more I'm realizing I don't think PWM is actually going to be refined enough to keep this actuator in a sort of variable lock position. It seems like it's either locked or it's unlocked. I think what I'm going to have to do is effectively apply the DC signal to the motor when it gets to a position by counting how far it goes with the pulses that come off the sensor and the actuator. We're going to have it stop, and basically we're going to kind of keep that into a certain range. And then when we want to go back to the zero position, I think what I'm going to do is basically trigger a 12-volt signal real quick and then have it bounce back. I also feel like inside of the exploded view, so we go back to the exploded view here, the little whirly gig down here is on the same shaft as this middle sprocket, this middle gear that transmits the torque from the input shaft from the transmission down to the front drive shaft. And I have to believe that just because of how this is configured here, the way this is rotating is going to want to basically unwind our actuator to a home position, the zero position, just from the resistance that it's going to get from turning in there. So that'll help it get back to the home position as well. So effectively what we're going to do with our control system is we're going to do a startup procedure that calibrates it based off of the current feedback with our little current monitor down here. And then from there, we're going to look at all the pulses from the zero position all the way up, and that's going to set what our range is across the whole sweep of the motion up to full lock, from 0% up to full lock. From there, if we want to go somewhere between 0 and 100%, we'll just basically proportionally adjust how far that DC signal moves the motor and stop the motor at a certain count level, and then assume that we're some percentage there. So we won't be able to actually check that until we create the control system on it. That's going to be in another episode because we're going to have to get real in depth with hardware and the software on it at that point. But I think at least for now, we've got enough understanding here that we're just going to use a 12-volt signal to go ahead and drive the transfer case actuator. We're not going to screw around with PWM. And basically what's going to happen is our controller is just going to pulse a full DC 12-volt signal to actuate this along the 0 to 100%. So that'll be in a later episode, but the good news is I'm super stoked because we've actually got to a point where I know enough about how this thing is operating that I can actually create a first go at a control system on this. And I'm kind of happy that we can abandon PWM because I didn't really want to have to screw around with that inside the controller anyways. And it's going to be a lot easier just to run this as a DC 12-volt signal versus PWM. And it won't make all the little frequency noises that you hear either. All right, that's a wrap on this series of videos about characterizing the ATC 300 transfer case and the xDrive actuator. Can't wait to get this put together in a control system and implement it into the E36. As it warms up outside, we're going to start tearing into the E36. We're going to get the motor and suspension dropped in the front, and we're also going to start taking apart the E46 donor car. So hit like and subscribe if you want to follow along. Also, I've gotten a lot of good input from people on Instagram, Facebook, and on the forums. So take a look for Adam PE21 on those socials as well, and you'll get a little more insight into behind the scenes and some more interaction live as we're going through and doing these updates before the videos drop. Thanks again for everyone's input. Couldn't do it without you guys and all the suggestions. It's going to take us maybe a couple of weeks, months, years, millennia. As long as it takes, I'm bound and determined to make xDrive work on this project, and we're going to make it happen. Again, we got E21 behind me. I got the Sonoma up on jacks. It's been up on jacks since November. We got to get that thing back on the road too. So in the meantime, we're going to be working on some other projects, and we're really going to tear into the E36 when it warms up outside here. Thanks again for coming along for the ride. We'll see you guys next time.